So it's kind of important when you're doing PSI to take care of yourself. You can work yourself into a corner, and it's going to happen. And it's good to take breaks and do other things, not take academics so seriously all the time. And so in that spirit, I invite you to come and join me today at 3 p.m. to go to the Kitchener Blues Fest. So what, if you want to come, what we'll do is that we'll meet downstairs at 3 p.m. and walk to the bus station. If you have your water card, it'll be free. Otherwise, I think it's $3.50 each way or something. It won't break the bank. And, the Blues Fest is free. And it goes over, it goes on through the weekend. So if you don't want to go today, you can go tomorrow. So just and in the meantime, you can even look up what's what's on offer, and if you want to go to a different time. So there's lots of interesting things, especially in Kitchener. I don't know why that happens. It's just a city next door. It's actually the same city. It's just like they're joined together. So I encourage you to do that. Next week, after the lectures, I'll go in the evening climbing, and Lauren will go with me. And those of you who want to try it out for the first time, or just like continue climbing, you guys can come with us. I'll give the details more later. Okay, awesome. So I looked up this reducibility business yesterday, and this is apparently, so a representation is reducible if it can be written in this form. If it can be written in an upper triangular form. So if D acts on the vector space V, then there is a subspace, invariant subspace W, that this form preserves. But the orthogonal complement of that space is not invariant. So this is an example of what is known as reducible. And fully reducible will have the form where you can actually bring a representation to a block diagonal form. So let me give you a very quick, before I go on to give you a quick overview of how Lie algebras arise from Lie groups, are there any questions? Yes.
And what about the word decomposable?
I'm not sure what that is. I think probably the fully reducible is probably, I don't know. Yeah.
Any conditions on D1 and D2? Do they have to be faithful, not faithful? Doesn't matter.
Right. I mean, I think I don't think there is. Yeah. For irreducible, they have to be a non-trivial representation. It doesn't even say if it has to be faithful. They just have to be like not the trivial representation. Yeah.
For the fully reducible, would D1 and D2 have to be irreducible representations? If not, you could have a reducible representation for D1 and D2, and then it would be fully reducible.
Sorry, can you repeat that?
Sorry. Would D1 and D2, if the fully reducible one, have to be irreducible representations?
Yeah, because otherwise you could actually do it further, right?
Yeah.
And but it could be.
Could be more than two, right?
Right. Yeah, it could be more than two. Yeah. Anything else? All right. So let's get on with it. So, given a manifold, say M, this is some manifold. There is really no natural way to define a vector, a vector field on it. In physics, we define it by setting some physical, fields on it or matter. So an example of a vector field is, say, fluids through some pipe or something, right? At every point in that manifold, you have the velocity of the fluid. But if I just give you a manifold, there is really no natural notion of a vector field. However, on Lie manifolds or Lie groups, of, say, dimension n, one can naturally define n vector fields. So if you don't know what a vector field is, it's basically some, every point you have some small vector which is smoothly varying. That's the heuristic. So in some sense, every point you have a tangent space, and you're specifying a vector on the tangent space which varies smoothly as you go from point to point. So we will see that. So how do we define this? So let's look at the tangent space at the identity element. So the tangent space at the identity element so analogous to the tangent vector that we defined, at the identity element, you can define a tangent vector in the following way. So I take one of these group elements and then take the derivative with respect to the parameter and then set the parameter to 0. And so there is no sum over A in this formula. So this gives me a set of n vectors at the identity. So I can think of these guys as tangent vectors at the tangent space at the identity. Now, I claim that there are n vector fields on the manifold. All I've shown is that there are n vectors, tangent vectors at the origin. So how does one extend these vectors to the whole manifold? Any guesses?
Lie derivative?
Exactly, Lie derivative, right? So the Lie derivative, we'll come to that notion, but I'm actually going to give you a different answer, and I'll make that claim without proof, but I think it's right. I just didn't get the time to prove it. So suppose, given one of the tangent vectors at the identity, you want to naturally obtain a tangent vector, say, at the group element G. then what you do is that you take this guy. So this group element, say, is given at, so this is a, so I believe that this is what you should get when you actually get, like, integrate the Lie derivative, which I have not introduced. So this will take you, so the underlying idea behind it is that if you have two manifolds, say M and N, and there's a map between these two manifolds, so which means that just any point here is mapped to some other point here. Let's call that map, say, psi. Then that map induces a map from the tangent space, or the space of tangent spaces, which is known as a tangent bundle, of M to the tangent bundle of N. So this map induces what is known as a push forward map, and this basically takes you from the tangent bundle of M to the tangent bundle of N. So, and these two manifolds, M and N, can be the same manifold. And in our case, that is exactly the case. If we have, like, we take an element, say the identity element, and we multiply it from the left by some other element, then we get to this. So you know, so left multiplication is a map from M to M. Okay? So the map, so the map that it induces on the tangent space is this one. That's my claim.
Is it a claim or it's just a definition? They're defining a map.
Well, so you know, okay, this is how I think. You may not agree with it. It's, I mean, it's clear that if this is a Lie algebra, then this is going to be a Lie algebra, okay? And so I don't see any other possibility, but as I said, I haven't actually worked this out. The best way to do this is to actually take the Lie derivative, integrate it, and find the integral, you know, the solution to it, right? But so I'm making this claim, but, you know, see if you can verify it, okay? Yes. Oh, okay, algebra. That's a good question. An algebra is, okay,
Vector space where we define multiplication of vectors.
right. So, yeah, so in this case, we will get to it, but, you know, for example, these matrices, they form a vector space if you, say, add to it the zero element, right? The null element. That much is clear, right? So then it's just a vector space, but on a vector, but these are also matrices, so square matrices, so we can multiply them together to get another square matrix. So, not only is this a vector space, there is the multiplication, a notion of multiplication defined, which maps you from the same two elements of the same space to the same two elements of the one element of the same place, right? So yeah, thank you. All right, so at the origin, we have 3 linearly independent tangent vectors. So if I take one of them and just, this is actually what is known as an adjoint action, which we will get to next. If you apply this action on those guys for all the G's here, so these are G's, right? If I do this for all the G's, then for the given tangent vector, I get a tangent vector, a specified tangent vector at every point on this manifold. And if I do it n times for the n different tangent vector of the origin, I get n vector fields on my manifold. Okay. So, in other words, for sigma a by 2 or a 1, 2, 3, we get we basically, this gives you the vector field for all G in big G. Okay, so the Lie Lie derivative, the name of Lie derivative just came up. What is a Lie derivative? I'm actually not going to define rigorously what a Lie derivative is. You will see that in the gravitational physics course in January, unless you want to look this up. It's not a very hard, or you can talk to me later. So as you know that on a curved manifold, if you have 2 vectors at 2 points, there is no natural way of comparing them. However, if there is a vector field defined on a manifold, then we can use that vector field to actually kind of drag the vector at one point to the vector at another point, and we can compare them. Okay. So this is what Lie found, is that this way of taking the derivative of y with respect to x can be expressed as a commutator of 2 vectors. So, a tangent vector is kind of a derivative operator, and so if you were to apply 2 derivative operator on a function, it would not give you another tangent vector. But it turns out the commutator of 2 of these vector field is a vector. So that's something that Lie discovered. Okay. So if we take these guys to be our tangent vectors, it turns out that this is going to be, this must be another tangent vector because it's in the same tangent space. So it must be some linear combination, and we choose those linear combinations coefficients in such a way that they're real, and we will make choices This is the physicist's definition. We make choices for these tangent vectors in such a way that there's an I here. Mathematicians choose them in such a way that there is no I there. So, this I kind of things come from the fact that we are thinking of matrices, and these are Hermitian matrices, and these are real numbers, and things like that. But, if the commutator of two vectors should be a vector in that space, it should be a linear combination. And that's what this equation is telling me. So there is a sum over C. So for the case that we are interested in, it'll turn out that this thing is a completely antisymmetric Levi-Civita symbol, but in general it's not. So this is called the Lie algebra. And the F coefficients are called structure constants. And note that the way it is defined, the structure constants are antisymmetric in the first two indices. The kind of Lie groups that we'll be interested in mostly, we will show that the structure constants for those guys can be chosen to be completely antisymmetric. We'll show that later today. So what does this Lie algebra actually mean? So what it means is that near the origin, you have these vectors, tangent vectors, pointing in different directions. Now you can use the exponential map, and you will get some, as you ramp up the parameters in the exponential map, you will get some curve along which, it moves you. It's the curve along which you have the one parameter abelian, subgroup. And say after a parameter distance of S, you reach this point. So this is your sigma 1 of 2, in this point at this parameter distance S. And great. So over here, you will have another sigma 2. So if you were then to go this way, which is along the, these are called integral curves of sigma 2, a distance t away. And here you will find some, and if you go again in this way, S, and you end up here, and if you go this way along T, end up here. It turns out that these, in general, this rectangle will not close. And the Lie derivative measures the failure of this rectangle to close. And you can think of it as a infinitesimal measure of non-commutativity. That's a hard word to say. So that's my spiel about how Lie algebras arise from Lie derivative. Note that there is nothing special about the identity element, at least not for the finite dimensional Lie algebras or Lie groups we are looking at. The tangent vectors that we defined at some other parameter position, phi, it's easy to compute that they satisfy the same Lie algebra. Because these are G and G inverses, they will cancel, and okay, that this reduces to this, and vice versa. Okay, what are the properties of the Lie derivative? Because we are, when these are matrices, they actually become just commutators. So a non-committal and politically correct name for these guys is the Lie bracket. If you get a bracket named after you, it means you've arrived in mathematics. There's the Lie bracket, there's the Poisson bracket, and there's the Dirac bracket. Dirac actually has more than one bracket named after him. The bracket notation, of course, which is very clever, but in mathematics, in geometry, there's a different Dirac bracket. All right, so on a typical say Lie algebra, we get something like TA TB, I of F A B C, T of C. So these TAs are called generators because they generate the group through the exponential map. So as I've already mentioned, the FABC, they're known as the structure constants. Rarely do you actually have to know the structure constants themselves. So on compact Lie groups, these are completely antisymmetric. The Lie bracket itself is antisymmetric. And the way we have defined the Lie bracket, which is the commutator, it satisfied what is known as the Jacobi, or if you're an English speaker, Jacobi identity. This is just a cyclic permutation. There are a lot of identities named after Jacobi or Jacobi, including one in string theory, which is important for the supersymmetry of the string theory. So now what we can do is that we can take these X, Y, and Z to be the generators and use this in the Jacobi identity. So this is, then we get a relationship for the structure constants. Sorry, for now I should write it like that. So the relationship that you get is it's careful not to make a mistake here if you're going to use this formula later on, which I will do. But you will make a mistake if you are rushing through things. So this is what the Jacobi identity implies. So an important comment is that notions of reducibility of groups transfer over to the algebra. So for example, if these guys, act on some two-dimensional, vector, then this can act on the same, vector space. Okay? Because there are just some kind of, they are just like, they are just related to the identity element. They're basically, these guys around the identity element is just for infinitesimal is just this thing. Right? So it's kind of obvious, but it's as matrices, they have the same dimensionality, so they can act on the same vector space. So in literature, especially in mathematics, if you have a Lie group,
Sorry.
yeah?
What were you saying here about with the
Okay, sure.
exponential? Why is this related to reducibility?
Okay, let me explain. Yeah. So I mean, so the exponential of I of theta dot sigma by 2. In our case, it's a 2 by 2 matrix, right? So it acts on some two-dimensional column vector, right? So what I'm saying is that the Lie algebra elements, which have this form, they're also 2 by 2 matrices, right? So they can also act on the same vector space. Okay, so
One is if it's invariant for the group, it's going to be invariant for the algebra as well. But
yeah.
you can expand it like.
So an important comment is that, so given a Lie group, you can always derive the Lie algebra. But if you're given the Lie algebra, the other way is not always unique. Getting to Lie group, and explicitly we will see this in the case of the SU2 Lie algebra. So the Lie algebra, let me write the Lie algebra of SU2 like this. This will take us to, when we exponentiate it, we will see that we arrive at two different groups. One is called SU2. The other one is called SO3. Okay? So they locally look the same, but globally they're not the same. And SU2 is said to be the cover of SO3. It's a double cover. We'll actually do this in painful detail, perhaps in Monday's tutorial. Yes?
the structure constants?
Yes, exactly. Yeah. I mean, this is a particular representation of the Lie algebra in terms of 2 by 2 matrices. That is not, but the Lie algebra is more abstract. So if I give you, if you of course exponentiate, we will see that SO3 matrix, the fundamental representation of SO3 are 3 by 3 matrices. So there is no way that you'd be getting a 3 by 3 matrix from exponentiating these matrices. So an extremely important concept in Lie algebra is the idea of the adjoint representation. But before we go to the adjoint representation, let me define what the adjoint action is. So this is the adjoint action. It's just conjugation. Now I'm going to make a claim, and the claim is the adjoint action on the Lie algebra of G by the group G form an irreducible representation of the Lie algebra acting on itself. Kind of a very cryptic statement. We will unpack it now. Okay, what does this mean? This defines something called an adjoint representation. So let me prove this fact. So let's define these to be, sorry, this is G inverse to be T tilde away. Then of course you can verify that this satisfies the same Lie algebra. So that means that we should be able to expand this object as a linear combination of the original Lie algebra elements. Oops, sorry, there should be B there. Because if TA is in the Lie algebra, so is TA tilde. That's what this statement is saying. Now let's take an infinitesimal element. Say G, then it's some identity plus I. Now since as theta goes to 0, we must have TA is equal to TA tilde. TA tilde is equal to TA. it must be that CAB should also have an analogous expansion. So it's the identity plus something that depends linearly on the same parameter, some object which looks like this, right? Yes.
Sorry, I just don't really understand how you can compute GTA G minus 1 since G is in the Lie group and TA is in the Lie algebra.
Right, they have the same dimension, so they're compatible as matrices.
I mean, they're not the same objects.
No, they're not the same objects like in abstract sense, but just if you think of them as matrices, they're compatible matrices.
How can G be a matrix?
So G we actually get by exponentiating the Lie algebra elements. So they must have the same dimensionality. So before we start, I'm not really sure how this was organized, the physics in nature groups, but our friend Arthur just arrived yesterday. Welcome, Arthur. And he is without a group. No pun intended there.
We had another arrival though yesterday.
Okay, so
I don't know.
okay, you guys maybe can form your like like a smaller group than the others, or you can attach yourself to two different groups. I guess I don't know what would be a
First time because actually it's on Monday, so wouldn't if they want to come, like, so more than happy to.
yeah. I mean, I think that's so because they've been thinking about projects since Tuesday night. So it's better if you guys like go and attach yourselves to some groups. Yeah, like they're nice people, so just okay.
I just
Remind me your name again.
Hi.
Your name?
Hi.
Haido?
Yeah.
Haido. Yeah, and welcome to Haido. Okay.
There also be one other person who may show up before Monday as well.
Sorry?
There's at least one more person who may show up before Monday as well.
Okay, well, the more the merrier, right? Yeah, this is like really a team building exercise. There's nothing to stress out about. The idea is to have fun. Actually, that's the idea. We forget that physics is supposed to be. We do this weird thing called physics that no one else does in the world, and we do it because we love it, and then we stress out over it. No. Anyway, so it should be clear why this should have the same infinitesimal form, right? So now if I expand both sides of this, the left-hand side gives me the leading term is TA, and then the subleading term is I, say theta, C, I think I made a mistake in my notes. 1 plus G, yeah. I sure did. Okay, so this should be then T of C, the commutator of T of C and T of A. On the right-hand side, we get delta AB acting on, delta A,
TA?
sorry? Oh, yeah, no, well, acting on TB, right? And then we have I of theta of C acting, and then we have A of BC, and it should be TB, right? So these guys cancel, and these are arbitrary numbers. So we are left with TA, TB, is equal to minus f a b c t of c. Sorry, not t of c, t of b. No, oh God, sorry. I meant c here, and I meant b here. Okay. So yeah.
So on the first line on the right there, so on the right-hand side, that's just CABTB, right? And then
Right.
on the left-hand side, are you expanding GTAG?
Yeah, I'm expanding that and keeping the term up to order theta. Okay, yeah.
So is the capital F the structure constant or is it something else?
It is something else. These are the coefficients. This is defined by this equation.
Okay.
So C's are the linear, coefficients of the linear combination. But because, in the limit where the thetas goes to 0, these two guys should be the same. That means that in that limit, the C should become the identity matrix, which is this thing. So to order lambda, this is some theta C times something. I have, sorry, there shouldn't be something, right? You had a question over there? Okay, thank you. Great. Okay. So now, what I'm claiming that f of c AB, I'm going to define the matrix f of c, whose matrix elements are AB, and that matrix element is given by minus f ABC. This is my definition. So let's pause. What is the dimensionality of this matrix if my Lie algebra is n-dimensional? N by n. How many matrices are there? N, right? So it is possible that these matrices FC form an n-dimensional representation of the Lie algebra. And that's something that we will verify, whether that's not true. It is unusual because if you think of the rotation of the two-dimensional, wave function that we discussed here, that was a three-dimensional Lie algebra because there are three generators there, but the matrices there are 2 by 2. So here we have the possibility of having a representation whose dimensionality as matrices are the same as the dimensionality of the Lie algebra. That's specific.
That it forms an irreducible representation because if you have SO2, then you're going to have a two-dimensional representation. It's Euclidean, so it could be.
Yeah, you can show that this is irreducible representation. Yeah. And yeah, this is something that we'll see that. I won't prove that fact, but for example, we'll see that the SO3 matrix, the SO3 group, is actually the adjoint representation of SU2.
Then in SO2, you have a two-dimensional irrep.
In SU2?
SO2.
Yeah, but SO2 is U1.
Yeah, but so you'd have a two-dimensional representation of SO2 from this construction you've created.
Okay. This is actually only valid for non-abelian Lie algebras. So where that would be an abelian case, yeah. Okay, so right. So I made an error somewhere in a minus sign, so something might mess up, but I think it should be okay. So what do these matrices have to be if this claim is true? Let's see if So if I say the structure constants FACB, if you define these to be this thing, I'm claiming that this is going to give you what we need. So okay, so in other words, so I'm using the fact that the structure constant is antisymmetric in the first two indices here. And this is my definition of these matrices. I've rewritten them so that the order in which these indices appear here is also the order in which these indices appear here. It's easier to memorize. So now what we need to do is to compute what these things are. Now, because we have them in terms of matrix elements, we need to take the matrix element of compute this. Now, do you guys want me to do this? We do, okay. So what is this thing? This is f of c acting on f of d minus f of d f of c, right? This is what this means. This matrix acting on this matrix minus this matrix acting on this matrix, and we are taking the AB element of this. Sum over repeated indices implied. Okay. So now we use a definition. So there are two minus signs coming from these guys, then two i's, so there's an overall minus sign. So minus CAE DEB plus, because there's a minus sign here already, f of DAE, f of CEB. So now what I've done is that I will write this, I will change some of the indices so that it has the same form as the Jacobi identity I wrote earlier. So we have CAE, f of DEB. The first remains the same, but this sign is now changed. And then this becomes FADE. So I have switched these two guys, and that picks up a minus sign. But this I keep the same. Now, if you go back to the Jacobi identity I wrote and painfully map the free indices here to the free indices there, and you will find that you get f of DCE, f of AEB, and which we can say that we can then switch these two indices, and then we pick up a minus sign, but that minus sign can be absorbed into I squared by writing it as I squared. So we have CDE AEB, and then we use this definition on this guy, the second guy. We have one I left over, and this left over, CDE, and we have minus I. The minus comes from the fact that we are now going to switch this to E of A, and this remains the same. So we have I of FCD of E, and this is F E A B. Right. So this is, so we have shown that the adjoint action gives rise to a representation which is the adjoint representation. So this is the adjoint representation. If I suppress the matrix indices, this is my adjoint representation. And this set forms an n by n dimensional. By here I mean matrix dimensions, E rep of the Lie algebra, where the dimension of the Lie algebra is n. So the adjoint representation is very useful. It allows us to define an inner product on the space of Lie algebras. So for example, suppose we have an element T A and an element T B. We can define some inner product as the trace of the adjoint representation of the corresponding matrices. Now, this is a real symmetric matrix. Why is it real? Remember how F is defined. Right? F is defined in terms of the structure constants. There's an I there. The structure constants are real. There are two I's in this trace, so therefore it's real.
We didn't necessarily define the structure constants to be real, did we?
Yes, we did. We can. Yeah, we did. So this is real and symmetric. Symmetric in A and B. Why is it symmetric?
It's a trace.
It's a trace, right? So that means that we can actually bring it to some diagonal form where K, A are the eigenvalues. So there's no sum here. And it turns out something I'm not going to show. In fact, I don't even know how to show it because I haven't looked it up. Is that if G is compact, then Okay, sorry. Before I go there, you can actually rescale the Fs. You can actually rescale the Fs so that the modulus of these eigenvalues are 1. However, the sign cannot be adjusted, cannot be changed by rescaling. So the number of different signs are invariant. And so for compact Lie groups, so by compact I mean that in some sense the volume of the manifold that describes the Lie group has finite volume. So, it's not, yeah. We will see Lie groups which are not compact. The Lorentz group, which you can just keep on boosting, right? And it's actually a non-compact. So for compact Lie groups, you can choose these to be some positive constant. So where lambda is 0, and then the trace of Fa and Fb becomes this. When you can do that, you can show that the structure constants are actually completely antisymmetric. So this implies that structure constants are completely antisymmetric. So, so let's just introduce the notation where we say FABC, we write it as F of ABD, just to make our life easier. We are not saying that B and C is antisymmetric, but we are just rewriting it so that they're on the same level. So, yeah?
Feel bad.
Yeah.
Yeah. What ingredient goes into showing that this representation is irreducible? You know? Because we explicitly build the representation, but what guarantees that?
Right. What guarantees that it's irreducible? Well, I mean, I guess you'll have to show that you cannot actually, there is no similarity transformation that brings it into diagonal form. And if it's a simple Lie algebra,
So for
yeah,
So it's not, so the way you define the adjoint is big A adjoint. But little a adjoint is always an irrep if it's a symbol. If it's simple. But
right.
big A adjoint is not necessarily. And that's what we were saying with SO2, and even like if you consider E8, the smallest non-trivial Lie algebra representation is 248.
Right.
That's the smallest irrep, and that's not dimension 8.
That's on what?
Or that's not, that doesn't seem like that's proper.
E8 has, it's rank 8.
Rank 8.
Yeah. But it is, what is it, 248 dimensional?
Is it?
Yes. Yeah, it is, SU2 has rank 1, but E8 is 248. Let me come back to your question. I'll think about it. I'm sure there's a simple answer. I mean, I've never actually done, prove this, but I'll just try this weekend and let you know. Okay. And if you figure it out, let me know. Unless someone has the answer. Okay, we'll revisit this question. Thank you.
I have another question.
Yeah.
Why does this imply that the structure constants are completely antisymmetric?
No, I'm going to prove it now.
Oh, right. Okay.
Yeah. So let's start with, say, working out the trace of the commutator of this times FC. Now, if I use the Lie algebra in the first term, I get trace of I of A, B, D, F of C, sorry, F of D, F of C. So on the left-hand side, we have trace of FA, FB, FC minus trace of FC, FA, FB. Okay, on the right-hand side, we can write this as I, F, A, B, D. These are just numbers, so we can pull them out of the trace. And then what we have is the trace of FD, FC, which we write as lambda of delta DC. On the left-hand side, what we can do is that we can use the cyclicity of the trace to write the first term. So here we had a commutator between A and B. Now we'll try to get a commutator between B and C. So first term, we can write this as F of B, F of C, F of A minus F of C. The second term, you guys are not paying attention, right? This should have been FB, FA, FC, right? Okay. So this I can do the cyclic, then this becomes this thing. On the right-hand side, we have I lambda F of A, B, summing over D gives me C here. In the left-hand side, I have trace of the commutator of FB and FC multiplied by FA on the right. This guy remains the same. And this thing is I times FB of C, D. Then we have trace of FD, FA. And we have I lambda F A B C. I'm going to use horrible Blackboard practices and right here. So this thing is lambda delta DA, delta AB, DA. So, but there's a sum over D. So I can replace that sum, the D by A. So we have, and the lambdas and the I's on both sides cancel out. So we have, in the end, FB CA is F ABC, right? Now, the left-hand side, we can use the fact that these two guys are antisymmetric to write this as minus F C B A. The right-hand side, using the fact that these two guys are antisymmetric to write this as FB minus FBA of C. Oh, hang on. F. So yeah. Okay, I didn't have to change that actually. Yeah, sorry. So I could have just like, okay, the left-hand side I don't need to change. So what we have seen is that the structure constants are antisymmetric in the last two indices. Okay? That's what we've shown. And because it's antisymmetric in the first two indices as well, it is antisymmetric in all the indices, right? So the structure constants are antisymmetric in all these indices, or as completely antisymmetric. Okay, so may I take, say, 10 more minutes that we lost, say, in the fire thingy? Okay, thank you. So let's start with some examples of matrix groups. I will give you a small list of matrix Lie groups, and then hopefully next time we'll do in detail the properties of two of the most often used matrix groups in physics. Okay? We will actually look at them in gory detail. Okay. So examples of matrix Lie groups. I had not come across Lie's name until I was in my master's, and it was during summer between undergraduate and my master's in Bangladesh. We had a summer QFT class, taught by a professor who, it wasn't like a credit course, but we wanted, so he gave us a book and we were waiting for him. I remember we had the chapter open to Lie groups. So perhaps the most like the master group, if you like, is the GLNK. So these are n by n matrices with entries in the field K, which in physics is usually R or C. And so the G and a very important restriction, the determinant of these matrices, let's call these matrices M, is not 0. Because if the determinant were 0, then you would not be able to define an inverse element. And this is a very, very general, group. Under multiplication, the G stands for general, L stands for linear. So this is the general linear group of n by n matrices. All the other Lie groups, matrix Lie groups, are subgroups of this guy. Then there's the SLNK. Essentially, it's the same. Everything else is the same, except instead of saying that the determinant is not 0, we say the determinant is 1. The SON groups, So these are group of rotation in a of a rigid body in n dimension, and these are spanned by, these are some matrices O, and they are orthogonal, meaning that the transpose of the matrix is the inverse, and their determinant is 1. The S always tells you about the determinant. S meaning special. So these are special groups. And then there are the UN groups. And these are n by n unitary matrices. So meaning that entries are complex numbers, and the Hermitian conjugate gives you the inverse. A subgroup of this is the SUN groups. When you impose the further condition that the determinant is 1. So I'm not gonna like tell you give you any list of what the generator should look like. We will actually do some of these ourselves. So let's start today, and in the next 5 minutes I will we will get started on the special orthogonal group. Actually, let's use this one. Saves a bit of time. So the special orthogonal group, SON. So suppose you have in n dimensions some rigid object. I'm not going to draw an axis of rotation in n dimensions because it's only in 3 dimension. Rotation about an axis makes sense. In higher dimensions, you have to specify the plane that it's rotating in. Right? In 3 dimension, because of the Levi-Civita, we have a number of planes and number of axes are the same, right? Anyway, so so we have some rotation of some object. So let R be some vector, and the rotation of this object around some point in some plane means that if I rotate it by some n by n matrix, its rigidity means that the length of this vector remains unchanged. Sorry. So when I'm writing R transpose R, I'm actually taking the dot product. And that's so this means that O times R, and here this is O times R transpose. As you know, that the transpose means that we have to change the order of the matrices there. So this means we have to have this for the length of this vector to remain unchanged. So in components, I can write this as ij, ik, delta jk. Now, a real n by n matrix has n squared independent parameters, right? But because of this constraint, not all these parameters are going to be independent. So how many independent parameters do we have due to this constraint? To answer this question, let's take a variation of this equation. So we're slowly changing the parameters infinitesimally. Then the left-hand side of this equation becomes Oij, Oik plus Oij delta Oik. The right-hand side is 0. Now this is symmetric in J and K. So there are two cases. When I set J equals to K, I get n constraints. When I set J is not equals to K, because of symmetry, I can take J greater than K without loss of. Then you can convince yourself that that implies n squared minus n by 2 constraints. Okay? This is a small, nice exercise for you to work out. So initially, I had n squared parameters. So if I subtract this number, I get n minus 1 by 2. So this is the number of independent parameters. So that means that the dimension of SON is n minus 1 by 2. So let's do some sanity checks. Yes?
We've got n plus n squared to get onto.
Sorry, which one?
It's going from the third bottom line there to the bottom line.
So if I do this, okay, so then I have n squared minus n minus n minus 1.
Oh, sorry.
Right, anyway, yeah, I do those mistakes all the time. No worries. All right, so let's do some sanity checks. The dimension of SO2, we know that we only need one angle in 2 dimensions to rotate. So here we have 2, yes, we have 1, right? In 3 dimensions, you know that you have 3 independent angles, so you should get 3. So 3, you get 3, right? Very nice. So what are the generators of this guy? So we are not going to have I, although you can introduce I's here, but it just messes things up a little bit. So I'm going to parameterize this group. So let's take a infinitesimal parameter. Then we would say, okay, it should have some form like this, where A goes from 1 to n minus 1 by 2. Okay? So, and let's take these things to be real. So I think if I were to, anyway. So and then we say, what does this imply for these TAs? Well, if you now expand this, then on the left, this 1 on both sides cancel out. And then to first order is you're going to have, should be an A, TA plus TA is 0. But these are arbitrary parameters, so it must be true that the generators are antisymmetric real matrices. There's a clever trick which makes things look a little bit more nicer.
Transpose?
Right?
Shouldn't there be a transpose?
Haha. It's antisymmetric. So there's a clever scheme of labeling. Physicists and mathematicians are so scheming. So where we use 2 labels instead of 1. But we say that they are antisymmetric in the labels. So if A and B go from 1 to n minus 1 by 2, the fact that it's antisymmetric shows that there are actually exactly the number of linearly independent matrices here is the same as the number of linearly independent matrices here. Namely this number. So this is a label. These are not matrix elements. But we know that these are, as matrices, they are antisymmetric. So if I can say, if I take one of these matrix and write out its CD element, it's going to look very CD. Sorry for that pun. So now you actually have an explicit representation of the generators of the SO matrices. And this is going to be a finite element is going to be given by that. And then if you are nothing else to do, and you can verify that the Lie algebra satisfy this guy by these guys, is given by this wonderful formula. Which it is actually wonderful. People don't realize it. So this is the now the
Sorry, where did we get this from, the matrix elements of the generators?
this one. So if we like label the matrices.
This condition?
Sorry?
Just from this condition that the transpose is minus T.
Yeah, this and the way that we have labeled this, right? It's basically it's antisymmetric both in its labels and its matrix elements. So this is not a Hermitian matrix. And because of that, we don't have eyes here. If we were to define our generators as being Hermitian, I mean, they're antisymmetric, right? Then, we would have eyes and, it would look like the other structure constant. So mathematicians, when they write down Lie algebras, they actually, they actually don't use eyes, but, then their, operators are slightly different from the physics choices. It seems to me that, anyway, they're both choices, but, I chose not to use Hermitian generators here. But you can. Okay, one last comment. Sorry, I'm keeping you here for longer than I wanted to. Is there is a relationship with ON groups and I just want to finish this so we don't have to come back to this group in the next lecture. So if I start with this, this equation and take the determinant, then the determinant of a matrix doesn't change if it's transposed, right? So this gives me this. So this means that as far as this equation is concerned, I have two choices. However, this sort of parameterization forces one of the sign on us. So for example, if I take an infinitesimal element, so by dot I mean this object is shorthand, and let's just choose zeta in such a way that this thing is just and zeros everywhere. Okay. Then if I take the determinant of this, right, the determinant is going to be, so so this whole matrix is going to be something like this, right? So the determinant of this guy should give me this thing, right? Do you agree? Okay. Okay, I think there's a. So I wanted to argue that this shows that. Okay, let me come. I think there's a logical flaw in this argument that I was going to present. Let me come back to that at the end of at the beginning of next lecture. Yeah, please.
Do you think there's a 1/2 factors that's missing?
Here?
1/2 quarter.
Here? Or?
So half of the matrix is a quarter.
Zeta by 2.
Oh, okay. Sorry. There's a 1/2 factor.
Yeah.
That should be here?
No, it should be, but then later you didn't use it when you wrote O.
Oh, I see. Right.
It's even more than that.
Okay, I see. So there should be. Right. Should be half or yeah.
The half.
Yeah. And then when
Determinant.
right when you have this, then you should be 1/4, right? Yeah. Sorry, I think there's some slight. I'm having a little bit of a cognitive dissonance, as they say, because my argument was that when psi goes to 0, this goes to +1, but this is actually should be just 1. So, and therefore, the sign plus sign is chosen for us. But I think that's not a rigorous argument as I'm thinking about it right now. So let me come back to that point. I want to kind of argue that this parameterization, tells us that, sorry?
Like the SON part contains the unity, so you can't expand that for the ones that had determinant -1, maybe?
Yeah, no, I do. Yeah, that's something. But what I have a little bit of having a trouble with right now is that the determinant of O should be 1, not 1 plus something.
Yeah,
but that's
you can
only
just,
first order.
Yeah, I see. Yeah, okay, right.
You can derive that exponential at the parameter equals 0. Then you get just take the determinant.
Right, at the parameter this, right?
Yeah.
Yeah, and then what if I increase the parameter from 0 to, say, some small but non-zero value, that determinant should still be 1. And that's where, so I actually I should have thought about it a little bit more carefully, but let me think about it and come back in the beginning of next lecture. I think there's, yeah.
What were you trying to prove, actually?
I was going to prove that, this shows that we have to choose this to be the determinant for okay, so the idea is that if I chose this kind of parameterization, then I cannot choose the determinant of O to be -1. Okay. Now, so if I say, okay, this is actually true, to leading order, then
But you've neglected terms of order, of second order anyway, right?
Right. Yeah, exactly. Yeah. So, yeah, that's it. So, because we are, I think, yeah, but let me just think about it a bit more carefully, because, what Leander is saying is that, in this expansion, we are only taking terms up to first order. And thank you, that's exactly the argument, is that we see that, it's actually, so we can actually drop this. And then we see that having assumed this form, we get determinant O plus 1, not -1. That's it. Thank you.
And that form comes from, why did we assume that form? What was the step?
It's kind of we have the exponential map.
All right.
We are thinking of the exponential map there. And that's kind of related to the fact that we are on a manifold. And starting from some Lie algebra, we can go to some finite element. So that's why. So, so you might wonder, what about the minus sign? They do play a role in physics. So, for example, in 3 dimension, parity operator, where you reflect through all the directions, that it does satisfy this as well, but the parity operator, the determinant of parity is -1. So in 2 dimensions, for example, the reflection operator is this, and that is also has determinant -1. And of course, you can show that by rotating, you cannot get to these, configurations, and you actually have they don't add to the dimension of the group because there is no free parameter there, but they add to the volume of the group, and they add to disconnected components. So, this is, say, for SON, this is the component connected to identity, but then there will be other stuff which are related by, say, parity, but you can't. Yeah, questions? So,
I just wanted to check on that bottom board on the left. Should A and B only run from 1 to n?
Yeah. Thank you. Anything else?
But the drawing, I mean, it is SON, the first one, and then the other one is...
Right, sorry, the first one is SON. This whole thing is ON. Yeah.
I'm just not really sure what you're trying to prove, but if you were trying to prove that you can only access matrices with determinant 1, you could just say, like, the determinant is a continuous function.
Yeah, that's
And
what I was
so-
saying.
Oh,
You don't have the identity in that.
Yeah.
Yeah.
Maybe you could mark that the determinant of the exponential is the exponential of the trace.
Yeah, it's
Trace of t is 0.
right. Right. So yeah, one could use that. And in fact, in SUN, I will use that. All right. Thank you very much for listening and participating.